Good afternoon, everyone. Today we have Dr. Dan Miller with us. Dan received his bachelor degree in physics from Michigan Technological University in 2011. He's been working with Raymond Shaw's experimental cloud physics and Michigan Tech. And in 2017, he went on to obtain his PhD in atmospheric physics from University of Maryland, Baltimore County. So since then, he has been a NASA postdoc fellow working on polarized remote sensing of clouds and aerosols, a position in both the climate and radiation lamp and the ocean ecology lamp with research that was intended to overlap with the future NASA plankton, aerosol, clouds, and ecosystem mission. Dan's research focused on the simulation of shortwave passive remote sensing clouds and the impact that realistic spatial and microphysical inhomogeneity has on retrieval of cloud properties. Let's welcome the speaker.
Hello. So up here on the slide is just an image from my first research experience ever. As an undergrad, I got to go to Germany and live in the Alps for a month, and we had a very in situ cloud group, very focused on making measurements of clouds in their environment. And we went and lived on this mountain because of orographic lifting. We could look at the clouds and they would just come to us. We didn't have to fly in a plane. This is just to emphasize that there are a lot of different ways of studying cloud systems. You can, go to the cloud. You can make a cloud in a chamber. You can fly in a plane, possibly interrupting the cloud as you're flying through it, or you can study them from space. And we have to square all those different views when we talk about satellite remote sensing of clouds, because the clouds in their environment and what the radiation in space and the satellites tell us can be different sometimes. So these are all just a short list of collaborators on a lot of this stuff who are at UMBC or NASA Goddard or NASA GISS at various times throughout my work. And yeah, I'm going to talk a little bit about how I use simulations of clouds and observations of clouds to square this, what is actually in the cloud and what do we see and think is in the cloud conversation. So why would we care about liquid water clouds? I think the biggest thing here is that there are three elements of the Earth system that clouds are dominantly impacting. One is that they cover about 20% of the dark ocean surface, and because the ocean is dark and clouds are bright, their radiative impact is dramatic and significant. And it has very little infrared compensation because they're low-level clouds, they're liquid, they haven't frozen. And so their net radiative impact is very strongly negative. It cools the Earth by providing this reflective blanket. And the other thing is that it has its microphysical properties. The droplet sizes themselves are largely determinative of the cloud radiative properties. So when you look at them from a remote sensing perspective, the droplet size and how strongly they impact the climate are intrinsically linked in very important ways. And in addition to that, the shape of the droplet size distribution can tell you something about development of precipitation and then the water cycle. And all of that is, the water cycle and the radiative impact, they're all tangled up in this rather intractable physical problem that we always have to be considering, which is that aerosols and clouds are intrinsically connected with one another. If you have aerosols in the presence of water vapor and enough the right atmospheric conditions, you can make clouds, but without that you may not be able to make clouds. So in addition to just saying that they cover up the dark ocean surface, if you change the aerosol environment, these are ship tracks down the bottom right, you can actually increase the presence of clouds and have a net negative radiative impact on the climate. And the other thing is that all of the precipitation processes are also tied up into this radiation conversation as well, because when the cloud does rain out, it's dark ocean surface again. And so it's a very dynamic system, and it has a lot of influences in terms of the aerosol system and precipitation development. So I'm just going to talk about my stuff throughout the beginning of this, which is that I developed a large eddy simulation, LES, satellite cloud retrieval simulator. Basically, an LES can if you can, you get enough computing resources, you can model all sorts of things. And I'm basically taking an LES that is at a dynamical scale that can model enough cloud physics to provide a reasonably good description of a cloud. And I'll talk more about that in a little bit. I got to apply radiative transfer to those large eddy simulations, and then create retrievals, and then do some comparisons with actual observations and with that LES. And if I have time, I'll go into some other interesting side projects that I've done since then. So this is the basic picture of what the LES looks like. So we're looking at, on the right-hand side here, is the total reflectance in the large eddy simulation once I've done the radiative transfer modeling. And so, and I also just, I can arbitrarily define what I'm viewing and like what kind of sensor geometry I've defined. I'm changing the scattering angle as I look across the side to side of that image. So maybe it's like a scanner, so it's looking at different angles, scattering back to the detector. And the main thing here is that when you look at total reflectance, you learn one thing about a cloud, and the polarized reflectance has completely different information that can tell you something different. And I'll get more into why the polarized reflectance is useful in a little bit. But it notably is very spectrally variable, particularly in the scattering angle range that I'm looking at here. But yeah, so it's built on this realistic LES simulation that has the appropriate spatial and vertical inhomogeneity that we expect for this type of cloud. And most notably, the LES has bin microphysics. It's not doing a 2-moment or 1-moment scheme or anything like that. It's actually modeling the collisional coalescence processes and droplet growth processes on a 25 or more bin size scale. So it's it's capturing an element of inhomogeneity that we don't often have conversations about. And I'll get into that a little bit more later. Yeah, so most of these are on a roughly 7-kilometer domain, so they're kind of small. If you, say, wanted to take these same simulations and do, microwave radiometer simulations, they're on the order of the footprint of some remote sensing techniques, so you can get into trouble. But when it comes to simulating something like, say, MODIS with a 1-kilometer spatial resolution or 500-meter spatial resolution, if you're talking about some VIIRS products, 7-kilometer domain is fine. You can model high spatial resolution information, like if you saw from an airborne instrument flying close to the cloud, or you could average up your reflectances and get something that is a coarser spatial resolution, like a satellite would see. And then all of the bin microphysical properties in terms of how the droplets are scattering are calculated from me theory. And each bin is treated as a separate scattering species. So they're all scattering at the same time, but they're all treated separately. We're using a vector radiative transfer code, so we get total and polarized reflectances, and we can learn some stuff from that. The other thing is that I used several different LES cases, and I have even more than this, but they weren't part of some of the major, like the broad cross-cutting studies. More targeted, specific stuff. But they sort of span different microphysical regimes that these low-level liquid water clouds occupy. So the main thing here is that I've got a case, this DICOMS2 case, which resembles this low-level stratocumulus. It's covering almost the whole cloud scene. The cloud fraction is basically 1. because it fits in that one dynamical regime, it also has a particular microphysical regime, right? The droplet sizes are relatively moderately sized. But if you go to a different regime, say a cumulus regime, so that the top two cases are cumulus, and you change the aerosol concentrations, and now you've changed the condensation nuclei properties, so more droplets or fewer droplets will form. And you say take a polluted case, you get a very large cloud fraction as well, fills the whole scene again. But the droplet sizes are really small because you're dividing up the same amount of liquid water amongst a whole bunch of different condensation sites. Then you cut back on the aerosols, and suddenly you have the other story where the cloud grows very, very deep and the droplet sizes get very large. And that's the clean trade wind cumulus case here. So this is the optical thickness and the effective radius, and this is the effective variance, and I'll talk about what these mean in a second. But they sort of occupy all sorts of different regimes, and so the idea is that we're capturing some element of different realities that clouds can occupy. And these are going to be my ground truth properties. It's not trivial to say, like if I'm looking at a column of a cloud, what's the droplet size of a column? You have to come up with some description of how the satellite will vertically infer that information. And I don't know if I have slides in here that talk about this explicitly, but even coming up with that definition is kind of difficult. So, so just a note, I guess. So I'm going to use those properties as ground truth. And this is just an aside. It's too mathy for sure. But the cloud droplet size distribution is typically described as a gamma distribution. One reason to do this instead of like a log normal distribution is that both of those things fit the observations relatively well. But the gamma distribution has a couple neat properties. They're just math properties, basically. And so you can actually write the gamma distribution up on the top there in terms of these important moments that are related to scattering. So this effective radius is it's the third moment of this droplet size distribution. It's a cross-section weighted mean size, if you think about it like that. And it's actually a parameter of the distribution, so that's convenient. But it also means that the effective radius doesn't actually define like mean size or anything like that. So it shouldn't be thought of as a mean size. It's a scattering weighted size. When the tail of the distribution is long, the effective radius is long. And the mode is actually somewhere less than whatever I say the effective radius is. And when you talk about liquid water clouds, everyone uses a radius. If you talk to people who do ice, they also use diameter. Everything in my presentation will be radius. The effective variance, however, is some people say it's the width of the related to the width of the distribution. It's kind of a misnomer, and it's kind of harder to describe. But it basically controls both the mode position in really significant ways. If the effective variance is very large, you get the distribution mode switch towards the smaller size regime. And if you get effective very small, you get basically a like a narrow Gaussian type distribution. Still log normal, or still gamma distributed. And if you plot it in log space, you'd see significant differences in the tail. But in linear space, it looks like it's almost a Gaussian. And so let's see. So the first thing is that there's a couple different ways of doing cloud remote sensing from passive shortwave platforms. Most notably, there's this bispectral retrieval technique. Some people call it the Nakajima King method. But you know, the authors of the paper, or one of the papers about it. And the premise is that you take a band that predominantly, in terms of liquid water, is scattering. So you take a band, say, like in the near visible, like 0.66 or 0.86 microns wavelength. And clouds there are very bright because they scatter a lot of light, and there's a lot of multiple scattering. So you have some significant sensitivity to optical thickness because it's so dominantly scattering. And then if you go to another band where, you know, instead of being dominantly scattering, there's a lot more liquid water. So say a band like 2.2, around 2.2 micrometers or 3.75 micrometers. There's a lot of liquid water absorption in these bands. And so you get sensitivity to droplet size because of cross-section absorption sensitivity. And you use the two of those together to tease out the interrelationship of optical thickness and effective radius from two different measurements. And a note here is that the total reflectance retrieval assumes that the effective variance is fixed. So you don't have any information about it. And if you did try to include it in your retrieval, it's a very small impact. So you just don't have sensitivity to the width of the distribution, if you want to call it the width. The basic premise of the approach is that it's a lookup table. So I've got these curves. These curves are calculated beforehand, and I've got a measurement of reflectance in two different bands, and they meet at that point in the star. And if you look at the colors of the lines, as you increase absorption in the SWIR band, you increase the droplet size because they're larger, they're absorbing more. Or as you increase the near visible reflectance, you increase the cloud optical thickness because it's brighter, scattering more. And the two of those pieces of information, if you're in a thicker cloud regime, are basically orthogonal, and you can do an interpolation and get the right droplet size and the right optical thickness at the same time. You get into bigger trouble when you start to get into the more nonlinear regime, when clouds are thin. But for the most part, this is the way this method works. There's always one retrieval for one viewing geometry. If you went and looked at that same scene from a different geometry, the lookup table would look different, but you might get the same answer or not. And that's the premise of the approach. The polarimetric method is, it's been around almost as long as the bispectral method. It's just a slightly more technologically difficult measurement. There are some reasons why it's actually easier, but I can talk about that later maybe. The polarimetric technique is you have to get a lot of different measurements of clouds at many different angles to be able to do this. So instead of just one fixed geometry in two different relatively separate spectral bands, this method requires maybe only one spectral band, but a lot of different angles. So here's an example from the Polder instrument. It's a French space agency instrument. It flew in the A-train on the Parasol satellite. And on the top right here is what total reflectance looks like from the Polder's perspective. It's a wide field of view imager. So it's got basically a wide angle lens. And the red lines in that image are showing the different scattering angles that this one snapshot is looking at the cloud from. But if you go to the polarized reflectance that they're also measuring from this instrument, and you look at side scattering all the way up into back scattering, you can see there's a lot of spectral variability in the cloud signal. And that's because right here you have a primary cloud bow, which is sort of spectrally neutral, kind of reddish, bluish, depending on what droplet size you have. That'll kind of change. But the primary cloud bow is just a bright white feature. Unlike the rainbow, they're related in terms of scattering properties. The color variation in terms of smaller cloud droplets is actually in these supernumerary bow features, where there are possibly many oscillations, and the droplet size and the wavelength change their location. And also, just to name a few more things, so primary bow, supernumerary bow, and then you've got your cloud glory that you can kind of see in the middle there. And also, in terms of Polder, you also see, at side scattering, you see all of the Rayleigh scattering associated with, just the atmospheric gases and maybe aerosols also. The other unique thing about polarization, and I don't think I'll spend any time talking about this too much, but is that the scattering information from clouds and aerosols is actually really separated in terms of angular space. So aerosols, because they're so small, are scattering a lot of their polarized reflectance into the side scattering direction. And clouds are scattering a lot of their polarized reflectance information into the near back scattering direction. And so you have those two pieces of information sort of spatially separated, but in an angular sense. And you can tease them out separately if you are very careful with your retrieval algorithms. The other thing to say is that your sensitivity to droplet size, so I'm fixing the wavelength here now. I'm not looking at the spectral variability. And if you fix the wavelength and you look at different droplet sizes, you see that the location and width of these rainbow peak, cloud bow and supernumerary cloud bow peaks actually move around as a function of droplet size. So your signal for the polarimetric retrieval is the shape of this curve. And if you could fit a curve to your results, you can get a retrieval. It's as simple as that. And then for the effective variance, your sensitivity is about magnitude of those bows. So when you have a very broad distribution, just like with rainbows, you have a very broad distribution of rain droplets, you don't see a rainbow, even if the sun is in the right location. And so same idea here, but for cloud bows, they get smoothed out and you don't have a signal anymore, both in terms of droplet size, kind of, and effective variance. So there's a possible retrieval bias here if you're worried about getting the right retrieval of droplet size as well. So you have these two techniques. We had two satellites up at the same time that were doing that kind of measurement. The natural inclination is to, let's just try to compare them. Like, are they looking at the same world? Are these clouds the same as those clouds from their different perspectives? And the techniques are so different that you may not expect them to be the same. But there was a study, Brayon et al. In 2005, they compared the two and showed that the MODIS-like bispectral retrieval was getting retrievals that were larger by 2 micrometers on average everywhere over the ocean than the polarimetric retrieval. And this was surprising because the predominant theory going into that study was that polarimetric reflectances are scattered. They're mostly single scattering. They're coming from the very top of the cloud. And if the cloud is adiabatic and the droplet sizes are increasing as you go into the cloud, the one that is most sensitive to the top should be the big one. And then if you go to one of these bispectral retrievals where there's a lot more scattering deeper in the cloud, the idea was that they should be smaller and not bigger. And so they found that, and it was later explored a little bit more. And the reason why the bispectral retrieval might be biased high is because of cloud spatial inhomogeneity. But in absence of that, if you go to an airborne study, so like this Airborne 2015, and you compare the two retrievals again, lo and behold, there's no bias whatsoever, and that correlation, I'm not showing it here, is something like 92%. It's a fantastic fit, and the two retrievals are basically the same. So what's the conclusion here? Like, how do we understand what is the difference between satellite view up above and the airborne view down below, and are we close to saying the same thing with two different methods, or are we really far away? And 2 microns actually makes a big difference. It might seem like nitpicking, but it's a big difference in terms of radius of impact of clouds. It's a big difference in terms of the onset of collisional coalescence happens after you get above a certain droplet size, and it doesn't happen if you aren't above that droplet size. So if you say that your droplets at the cloud top are 20 micrometers, or you say 18, that means something. That's important. And so the other problem is that these two comparisons are, well, both of them are using different instruments. And the satellite measurement is on different spatial resolutions and comparing them, aggregated up to the same resolution. And down here, the airborne measurements are maybe not pointing at the same target all the time because they're on different wings, and the wings flex when the fuel changes. And that's an important thing to consider. So are these comparisons the best versions of themselves? That's also a problem. The idea with the LES is to get rid of all of that. Like, your satellite is limited to whatever, engineering limitations it has, measurement limitations it has. If I can model the LES as close as I can and keep the retrieval algorithm and the model radiative transfer consistent, everything's at least in the same universe, same coherent box. And if I compare these two things now in that same coherent box, it might not be the real world, but I am saying something realistic about the retrieval methods. So the point of this study is that I took the LES and I did all of my remote sensing stuff, and I got a polarimetric retrieval on the y-axis and a bispectral retrieval on the x-axis. The bispectral retrieval can't get results below 5 microns, so there's a hard cutoff. They lose sensitivity. And there's also not a lot of cloud droplets below 5 micron, which you can kind of see in terms of the polarimetric retrieval. They only go down to like 3. And these are, just to emphasize this is a log density plot. So if you see red somewhere, almost all of the retrievals are in that regime. And if you look at the mean biases and correlations, the story is basically everything is near the one-to-one line, and there are some deviations from it, and you have to come up with explanations for those. So first of all, we found right away that if you limit yourselves to thicker clouds, like I said, the nonlinear shape of that bispectral retrieval, the thin clouds can cause some problems. If you limit yourself to the thick clouds, and you limit yourself to cloud droplet size distributions that are relatively narrow, then everything basically looks the same as the airborne study. So the conclusion from this LES simulation study is that something's different about the satellite perspective than from the airborne perspective. So these two retrievals are actually seeing the same cloud when you look at them close up. So what's different? So this is part of that same study. I looked at, if I take, say this is my LES, it's not, it's just a picture. And I have different coarse resolution satellite pixels, so like 1 kilometer or something like that. Within that 1 kilometer box, there's a lot of variability in the cloud brightness. And it's, that can cause some problems. And so if you look at different spatial resolution pixels, so 50 meter is the native LES resolution, and 800 meters is as close as I can get with an even division of the number of pixels to 1 kilometer. And if you look at, as I change the spatial resolution and as I look at the homogeneity of the pixel, the important point here is that this index here, H sigma, it's the standard deviation of the reflectances in that box divided by the mean. So when there's a lot of variability, the number gets bigger. And so the redder these points are, the more inhomogeneous the pixel is. And so when the pixel is more inhomogeneous, and when you make the pixel size larger, they get more inhomogeneous too. So those two things lead to larger biases when you compare the two retrievals. And so the story is that it's actually not that the clouds are different. When you look at the satellite perspective, it's actually that you have to deal with another practical problem before you say your retrieval is right. And here's just a picture overview where I show one of those retrievals, the lookup tables, and then I plot all of the subpixel reflectances inside of the lookup table. So that's all these dots here. The color of all the dots is the actual droplet size. So you can see they're all kind of the same color. So all these share the same droplet size. But the mean reflectance, this 800 meter observation, this is what the satellite would see. And if, you can tell right away, it's on a different RE line. So the droplet size from mean reflectances from the satellite resolution perspective is 23.6 micron. But in reality, if I took the mean of all of those subpixel droplet sizes, it should be around 18. And if I took the mean of the actual retrievals at that resolution, it's also around 18. So it's actually just a spatial aggregation issue. And it's because this lookup table is more or less nonlinear, depending on how absorptive the band is and how inhomogeneous the optical thickness in that pixel is. So this is also to say this pixel is 100% cloudy. If you make the pixel partially cloudy, it gets even worse because you're averaging just 0 zeros into everything. And you have to be very careful about that and flag your data appropriately. So the other thing is that if we move away from this LES study and you start to look at actual observations. So I worked a lot with this instrument called the Research Scanning Polarimeter. It's not an imager, it's a scanning instrument. So it looks in one direction and then scans really fast forward and backward from an airborne platform. It's the prototype of the NASA Glory mission. And unfortunately, it didn't reach orbit. So this is what we have is 2 of these. And they've done a lot of great science even still. So basically, they measure both the intensity, I, and the 2 linear polarization Stokes components, so Q and U. And you can use that to calculate degree of linear polarization or angle of polarization, whatever definition of polarization you want. And it has a lot of different spectral bands. And so you can learn a lot about aerosols and clouds from this instrument. And the other really key thing here is because it's a scanner and not a swath imager, it gets a lot more view angles. So there's about 150 different viewing angles that it gets for a single piece of ground real estate. And because it's on an airborne platform, it can also get pretty high spatial resolution just by flying close to the cloud. And so basically here is that it's just on top showing the scan swath as it flies over the cloud and the different views from each different plane location that give you the same target from different angles. And yeah, it's got a bunch of on-platform calibrators, and it's been very useful for a bunch of different types of studies. This slide can be intimidating, but just look on the left right now. This is what their data looks like. It's kind of confusing because it's not an imager. You're used to seeing an image and knowing what you're looking at. This is not easy to understand. Basically, on the y-axis of these plots is view angle, and organized in terms of sectors, but it's actually changing depending on how the plane is flying, right? So they organize them in terms of these view sectors, and what you're seeing in the top here is total reflectance, not changing very much as a function of angle. And you can kind of see a little cloud bow here. There's a bright spot. In terms of total reflectance, you can sometimes see a white cloud bow, but it's very weak. And in polarization, you can definitely pick out the cloud bow, and you can see that there are all these supernumerary bow oscillations. And in this particular scene, there's aerosols above the cloud, pretty significant amount. And so you can see a lot of molecular and aerosol side scattering. If you look at those and you pull them out and look at the different wavelengths, with this instrument you can do both, because it's got a shortwave infrared set of bands, you can do both retrievals. So you can do both the bispectral retrieval and get cloud optical thickness and effective radius that way, or you can do the polarimetric retrieval and get the cloud droplet size and effective variance. And then to get optical thickness, you still have to go back to the Nakajima King style retrieval, but you have the effective radius correct, and so you can get a better result that way. And the other thing here is just to emphasize that aerosol properties are almost all changing over here. There's very weak impact on the cloud shape, so you can still do your curve fitting retrieval and get an appropriate result. So I was working with that data, and I was working specific. So this is for my postdoc. I was trying to see if I could learn something about the aerosols above clouds in the Southeast Atlantic. So this is from the NASA Oracles mission. We were flying over top of this near permanent stratocumulus deck that's basically almost always there. And there's a lot of agricultural and natural fires in the fall, our fall. I don't know what season it is for them. Their winter, I guess. Winter, spring. So there's a lot of natural fires over here, and all that smoke, because of just the general circulation, gets lofted over top of these clouds. And the clouds are low, and they're boundary layer capped, and the aerosols are just stuck above. And so you get these pretty common occurring incidences of aerosol directly above cloud, and that can be a problem for remote sensing that doesn't assume that there's any aerosol in between the cloud and the detector. It can also be a problem for anyone who wants to do aerosol research, because all of their aerosols are above really bright things. And many of the aerosol remote sensing techniques have trouble handling that. And the other thing is that after you go some distance away from the coast, the aerosols eventually fall down into the boundary layer. And what impact does that have on the clouds? So this field campaigning is all to tease out all these different elements of that. And this is to show just where we were during Oracle's 2016. NASA had to leave Namibia for the later years of the mission, and we were actually up here later on. We're measuring different regimes of that cloud deck that's actually there. And the big point here is that while the study that I had talked about with the LES showed one thing. It showed that if you look at the airborne studies, things are basically okay if you go to high spatial resolution. the conclusion here is that, and this is doing the same retrieval from the same instrument, at least all the instrument characteristics are the same. You can get something that, and these are also pretty good in terms of mean bias. They're within the micron regime. Their correlations are pretty high, and also if you again remove only the thick or only the thin clouds, get rid of those because we know that one retrieval is going to do very bad in that regime. They're very similar to one another, and this is largely because in 2016 we're flying right over the top of this really thick cloud deck that's almost always there. When we went to 2017, we're flying in the transitional regime where it goes from closed cell stratocumulus to starting to precipitate. So we were seeing different cloud regimes and seeing a lot more thin clouds actually. And so if you go to this 2017 case, it actually looks more like the satellite. So the lesson here is that comparing these two retrievals and understanding the two of them, it's not just about satellite resolution. It's not just about satellites or airborne studies. It's actually about how spatially inhomogeneous the clouds are in the first place. And if you're starting off with a lot of thin, broken clouds, you're going to be in trouble basically all the time. Yep. And over here is just, if you take the optical thickness retrieval and you look at the bias of the effective radius, almost all of the really big biases are coming from the thin clouds. And it's largely because the bispectral retrieval has this problem. So the other thing is that you got these two techniques. They're using two different pieces of information, and they get you something similar if things are homogeneous. So we were curious, can you mix them together and perform a retrieval that uses both types of data? So the reason for doing this is I joined the Oracle's group after it had already started and there was already this project going. But the reason to do a neural network retrieval is that you can do it quickly. You can do it with relatively limited assumptions as long as you create a training set that's large. And you can use it to speed up a better algorithm. So the motivation here is to get a first guess for an iterative, physically rigorous, optimal search algorithm. So the other thing is that this particular type of retrieval we were doing on just the clouds with these two different types of reflectances, there are other retrievals we can compare to, right? We had all of this to know, like, if we get results that are within that root-mean square error, we know we're on target. When you play with a neural network and you try to do neural network inversions of any kind, if you don't know what you're aiming for, then you really don't know how to use the data, and you can't find when it doesn't work and why it doesn't work. It's hard to tease out. And yeah, so this is an explorative exercise, and the main thing here is that, and this is in our new paper that's supposed to come out soon, is that when you train a neural network and you work with a neural network that has different types of data, you can get into trouble if you don't appropriately provide the network with some extra information. And that is that for total reflectances, your order of magnitude is between 0 and 1, and it tends to be 0.1-ish on that order of magnitude. But degree of linear polarization is 0.001 scale. It's a very small magnitude. And then to top that, the uncertainty in degree and total reflectance is large. It's on the order of 3%. And degree of linear polarization is an order of magnitude lower than that. So you have to tell the network when you're training it, this data has this weight, and this data has this weight, because we are more certain about this data and we're less certain about that data. And if you just train the network on regular, just gave it all the total reflectances and degree of linear polarization data, it wouldn't apply an appropriate weight to the certainty that it has about that total reflectance, because it's a large value. And I can come back to this if anyone has any questions about it, but basically we have a deep neural network system that is taking in a very large data set of all the different wavelengths and all the different scattering angles in total and degree of linear polarization. And it uses that data to try to to minimize this cost function and search for the appropriate retrieval. And first we train it so those weights can get calculated, and then we put in real data and it does the same thing again. The main thing here is that we found that it worked relatively well, considering we were kind of naively just throwing stuff at it. And so in terms of the mean retrieval, it's kind of in the ballpark, and for droplet size and also for optical thickness. There are some anomalies that can exist. So for example, when you provide data to a neural network, you actually add noise to it so that it can search all the different possibilities if your measurement wasn't exactly accurate. When you do that, you usually do Gaussian noise. And when you get Gaussian noise near zero, you start to have negative values. And it'll still search for a result, and it'll give you something, but there are some negative optical thicknesses that can exist, and you have to clean those out if you're going to try to provide it as a data set. And it's non-physical, right? So if you were going to use this to feed into another more complicated retrieval, you got to definitely get rid of that. It's not going to lead to anything useful. But also you can tell that if for these training grids, you can do really coarse training for neural networks. And the only thing to tell you that you're doing it wrong is if you go and look at the data and you find that you have problems. So that's actually what we found here. We did a relatively simple training set that had very few droplet size bins and very few optical thickness bins, and not optical thickness bins that weren't actually spaced well for the distribution of optical thickness that we were going to observe, unfortunately. And so as a consequence, you can see that the binning of the optical thickness, where these peaks in the neural network retrieval show up, are actually really close to those bins. And there's a way to get around this, and we're implementing something new in our latest version, where you, instead of sampling bins, you sample a distribution of possible cloud and aerosol properties. And so you show the network a lot of different types of things. It learns more from that, rather than being fixed to one single bin for all the possible occurrences it sees. This is just an example of time series data. And the big point here is that when you train a neural network like this, we're getting roughly the quality of in terms of root mean square error that we saw from the actual retrievals when they compared to each other. So I guess the big picture here is that there's a little bit more noise and it's biased by a little bit, but this type of thing is possible, and we're looking into it more deeply now. This study was just to show you could do the cloud part. The cloud part's the easier part and the thing we can compare to. The idea in the future with this neural network study is to look at the aerosol above the cloud also. So provide an output from the neural network that says something about properties of the aerosol. Knowing that we can do this cloud part, if you can do this fast neural network inversion it's not an inversion at all. If you can do this fast neural network approach and get a guess for your optical thickness of the aerosol above the cloud, you can plug it into an algorithm that would take normally 3 hours to find the best possible combination of cloud and aerosol. But because you started that algorithm at close to the right answer, it'll converge much more quickly. And for optical thickness, we're basically bang on. But you run into issues. So this is from 2017. And this is just a comparison that shows, if your data has, physical flaws that are just always there, you can't do anything about it. So the big thing here is that clouds aren't spatially homogeneous, and light scatters from one part of the cloud to the next. But when you do cloud remote sensing, usually you say, this pixel is this pixel, and that pixel is that pixel, and they don't talk to each other. And if you did make them talk to each other, you have a much more complicated retrieval algorithm on hand. And it's not something we usually work with in terms of operational cloud retrievals. So the big thing here is that when you have a cloud hole, and so here the cloud optical thickness goes to 0 as you transition from one cloud over here to a different cloud over there. And the sun is somewhere off at some angle here. And so some of the light that scatters in that cloud is actually getting transmitted back out the side. So that cloud reflectance is smaller than we think it will be, because some of it's scattering away. And as a consequence, the droplet size blows up. Both the Nakajima King retrieval, the bispectral retrieval, and the neural network do that. And it's because they're seeing the reflectances that exhibit this 3D radiative effect behavior. So basically, we're throwing in, polarized reflectances that make sense because they're mostly single scattering. They don't scatter a lot out the side of the cloud, and it doesn't really matter. So the polarized retrieval is smooth and consistent right to the cloud edge. But the bispectral retrieval and the neural network, because they're both taking in that wrong data, that data has that flaw, the 3D radiative effect in it, they both run away. And when you transition from relatively thin cloud to very thick cloud, you can have very bright scattering effects as the bright cloud scatters out into the darker cloud. And that's called radiative smoothing. And in those regimes, the neural network actually struggles quite a bit to square the peg that you give it. This is just a side project without spending too much time on it. Because RSP has so many views, you can do a bunch of different interesting things with it. Just on not on an operational, like this is our cloud product type sense, but maybe on in a case study sense. So this is a simulation that I put together for one of my friends at GISS, Mikhail Alexandrov. He had made this algorithm earlier that used the tangent views that RSP gets. So all the views of the cloud where you see a cloud edge. And if you think about a cloud as a 3D feature, all those tangent views tell you about the boundaries of the cloud at different angles. And if you draw all those tangent lines, it's a bounding box for where the cloud is. You can think about this as like kind of a 3D or vertical cloud fraction. So that provides you some information about where the cloud is. And if you take the views that aren't tangent and you co-locate them along the cloud side, then you have the possibility to do this polarimetric retrieval right at the cloud side and say that this is where in the cloud's vertical profile I'm looking at. And if you do those retrievals, you get that red line on the top there in effective radius on the left and effective variance on the right. And if you take the actual cloud profile and you trace along the location that you say is the co-located location of that retrieval, you actually get something that's pretty similar. And it's actually very good at the effective variance and not so good at the effective radius. And there's a reason for that too. And it's actually because, and this is the thing that I see in the LAS simulations a lot, and we actually see in real observations quite a lot too, is that at cloud top, the dynamics of mixing, the turbulent nature of the cloud top, actually leads to multimodal distributions where you have very small droplet sizes and very large droplet sizes in the same distribution. It's actually two different modes. And this is a retrieval technique that Mikhail has that he calls the rainbow Fourier transform. In very simple terms, if you use a Fourier transform, you transform from your time series space to your frequency power spectrum to amplitude space, right? This method takes you from reflectance as a function of angle space, the angular signal space, and transforms to size distribution magnitude. So up here, these are his droplet size distributions in the, this is the actual LES droplet size distributions. And this is what his rainbow Fourier transform retrieval infers that they should be. And so if you compare that to this is just giving you one single number. This gives you the perspective of, oh, what is the shape of the distribution? Is there more than one mode? And actually, it does a relatively good job of capturing the multimodal behavior at the cloud top, and maybe not the relative magnitude of the two. This is actually something you might expect, though, because the cloud droplets that are larger are scattering more. And so your information about the large droplets is greater than for the small droplets. And if you look only at the droplet size mode that's the larger one, the one that you're more sensitive to in terms of scattering, you actually basically nail the vertical profile of the droplet effective radius. And then this is another point, which is that when we assume that the droplet is just one thing all the time, the gamma distribution, we can get thrown for a loop sometimes. And one of the things that's really nice about polarization is that it does give us the possibility of doing this type of thing. The rainbow Fourier transform, future polarimeters, when they're up in space, depending on the number of angles, you may or may not be able to use this type of approach. Just like with a time series with really low spatial temporal resolution, you might not want to use a Fourier transform to learn about the high resolution variability. Yeah, this could be the same kind of thing. So you would have to use this method on an instrument that has very high angular resolution. But actually, another thing to mention about this is a towering cumulus case. This is just before it starts to develop ice and start to precipitate pretty heavily and collapse. And the reason we were looking at this is that the RSP instrument flew during the CampX mission recently. And they were trying to basically do the same exact type of observation by planning the flight beforehand with these simulations. So the simulations can do, they can both be a research tool and a field campaign planning tool. This is just my summary slide. I don't think I need to read it or anything. I kind of summarized everything as I went. If anyone has any thoughts about how to use the LES simulator in different ways, I've got all of the data, and generally, if folks are interested in looking at clouds from a different perspective, I'm looking for collaborators all the time. So that's it.
Questions? So have you been able to looking at some longer wavelengths and the microwave?
Yeah, so I did some radar simulations actually really early on. In terms of microwave, no. There are some collaborators that are supposed to be working on some instrument comparison studies for ANCCP, this future NASA mission stuff. But yeah, the problem for some of them is that the spatial resolution of their spatial domain of the actual LES simulation is kind of small for their types of retrievals. But it's one of the things we want to do. Yeah.
Do you have the reference for the radius transform model you used?
Yeah, it's Dahan et al. I don't know what year it is, but it's the NASA GISS polarized vector radiative transfer. It's a polarized doubling adding code that if you go back to any of the GISS papers from the 70s, they're using the first version of that code. Yeah, and it's been updated since then. There's a lot of different modules that they've added to it. It's particularly good for cloud radiative transfer because it can be quite fast.
Is this model also include the aerosol?
Yeah, you can include aerosol. The LES simulations I did here were all cloud only and already subtracted ground reflectance, basically. So I was working with the best possible remote sensing situation and seeing how the remote sensing techniques behave relative to one another alone. Yeah.
So the model itself for the 4 stock vectors, the 4 component.
Mm-hmm.
Okay. And
yeah, it doesn't get V. You could get V. They just don't record it.
Yeah. And the surface is either any kind of surface have like a BRDF model or
yeah, you can do BRDF models. You can do. They have some pre-built libraries and stuff that for vegetative surfaces and stuff. In my studies, I wasn't using that feature, but you can do all sorts of stuff with the surface. They also had built this. So as part of the Glory mission, they did a lot of improvements to that code to get it ready to be the simulator of record for the instrument. So it mimics RSP data pretty efficiently. There's basically a flag. You can make the same type of data, and so they basically got it ready to be the algorithm that they would use to do their retrievals. And so it's a pretty robust code.
Okay.
Mm-hmm.
So the code is publicly available is just for the
Publicly, I think in the sense that if you ask someone,
someone.
yeah,
Okay.
they'll give it to you. If you reached out to Bastiaan van Diedenhoven at NASA GIS or Brian Cairns at NASA GIS, I think they've shared it with people before. I have it because Jibo asked him for it, so I think that's
Okay.
the main thing.
Okay, thank you.
Okay, let's wrap up and thanks the speaker.
By the way, this code also work for the UV?
I think it can.